And we're live. Welcome everybody. We're back. We're with Katy Salamati. Salamati, sorry. She is the Global Internet of Things Solution Lead at SAS. She has over 15 years of experience improving infrastructure and transportation safety and mobility through applying innovative IoT, AI, and advanced analytics solutions. It's a great pleasure to have you, and I'm
Thank you.
really curious to see how you're saving lives and helping people stay ahead of these disasters.
Well, thank you very much for having me. So today I'll be talking about the solution that we've developed with leveraging streaming AI and analytics for predicting and preparing for floods. So essentially, floods has been a natural disaster for a very long time, but we're getting more and more interest on solutions that would help us with being able to predict flood. So in terms of the fact and figures, there are three very important facts about or figures about this. 1 in 4 people are at the risk of flooding. Flood is the number one frequent natural disaster in the world. And the most recent study of 2021 showed that there has been a $54 billion impact, economic losses as a result of the flood. So in terms of floods are the most common natural disasters. According to their account for 80 to 90% of all the documented disasters from natural disasters. We've experienced this in US, across Europe, Middle East, Asia, Africa, so it's very universal. The 2019 Global Natural Disaster Assessment Report showed that the annual average frequency of major global natural hazards from 1989 to 2019 has been about 320 of them, and it shows that they're now increasing. So we've seen a tremendous amount of increase in flooding events the past recent years. And then the next one is $54 billion economic losses. That was the most recent report. This is just from Europe. Between 2018 and 2022, economic losses of the flood have been about $299 billion across the world. And so that $54 million has been only for Europe, but we see tremendous impact and tremendous cost to the infrastructure, to human lives, and to economic values as part of this natural disaster. And then 1 in 4 people around the world are at the risk of flooding. So flooding does not discriminate, for the lack of better terms. It actually impacts everybody everywhere. And although flooding can be common during the summer times, but it really happens throughout the entire year. So it could be winter storms, could be snow melts, could be river overflows, rain events that would impact flooding. And one of those major factors are urban developments that would impact and increase the risk of flooding, mainly because with the urban development, we're changing the landscape, we're changing the type of the soil infiltration rate. We are taking out soil that can absorb water and put in pavement and parking lots that don't allow any water to go in. And so that's one of the major causes that of this not being able to manage the flood or water in the as it's the right way, and therefore cause urban flooding. And so what happened? The SAS Flood Prediction and Preparedness Solution, something that we developed as part of the SAS Analytics for IoT collaboration with Microsoft Azure and LoRaWAN, which is a low-range communication network. We've developed a solution to be able to protect, respond, and improve to flood events. In terms of the protect, really it's all about improving citizen safety and emergency services with real-time visibility and flood predictions. In terms of the response, is about reducing the impact of flooding incidents on properties and infrastructure, or automating and streaming this response. So we are trying to predict faster and better, so then the response can be better managed and could happen faster. And then it's all about being able to improve the whole emergency planning and situational awareness around flood events, given the past historical data, given the current condition of the flooding and rain events, and also future forecasts of predicting where the floods needs to happen. So the dashboard that we have and the solution that we've created includes has multiple options and capabilities. Essentially, looking at it, it leverages a network of sensor data to be able to predict and understand really what's the current condition is. So bringing that situational awareness, and then combining that with AI and machine learning models to be able to forecast what the water levels are going to be, and also most importantly being able to forecast inundation, which areas will be inundated and how much they will be inundated. So we are employing machine learning or auto ML capabilities to be able to provide a very accurate capability. And so essentially our approach is to create a digital twin. If you think about digital twin, the definition of the digital twin is really a virtual presentation of the real world entities and processes. And what we've tried to create is to create a digital twin that would simulate water movements around the city or around urban or suburban or rural areas on the ground, and run the simulation every few minutes. We're actually running that every 10 minutes to be able to better understand how this water is moving from one section of the ground to another section, or from river to other areas, and also predicting where it would go in upcoming hours. So on hourly basis, up to 12 hours, we provide this accurate forecast. And so we are trying to create this digital twin of water movements to be able to better predict which areas will be flooded. The model that you're using, it's really what we call it is a rain over grid. So this digital twin capability is created for every cell of a grid. And the data that goes into it includes, water levels relative to Earth's elevation. So the elevation is very important. It's an important factor that would dictate how the water moves from, if you think about it, from one cell to another cell of this grid. Then the soil infiltration rate that would dictate how much water will go down or will be absorbed. The flow resistance offered by land cover, if there's flooding that happens after wildfires because of the land coverage that we lose as part of the wildfires, or the vegetation that would hold the water, runoff due to impervious areas. And these impervious areas examples are such as parking lots. Again, that when we build parking lot in a location that used to be a creek or was land covered, dirt covered, that could absorb water, that changes the dynamic of the water movement. The stormwater capacity system has an impact. Many of the cities, their network of stormwater capacity has been might have blockage. So depending on the capacity of their stormwater network, how much of that water could go down, and then how much is blocked and will stay on the roadways. Also, the rain levels from snowpacks or other factors. Environmental sensing goes in. So all these different factors goes in into be able to identify flood-prone areas, and also being able to predict what the water level and flood impact is going to be. So as you see, as I mentioned, we've developed this rain over grid model, which essentially divides the area that you're interested into various different cells of various different sizes. And then we are adding in all these data sources that are mentioned into each of these areas, and we're simulating for each cell. We're simulating every 10 minutes. Based on the sensors, based on the forecast on the rain, based on all these other factors, how much water we're getting, how much water is going down, how much water is moving from one cell to another cell. So it's a very heavily computational, essentially, approach to creating this digital twin of water movements and flood events for being able to better predict the impact of this natural disaster. Additionally, there are capabilities that would provide, what if scenario analysis. So what if we're not getting, we're getting more rain that is in the forecast, what if this road gets closed, or what if the storm capacity network or canals are more blocked than what we expected it. So all these factors going into trying and testing different scenarios. What if this road's closed? How I can get my resources around to be able to respond to these homes that will be flooded. And so we're trying to provide that prediction several hours ahead of the time, so the emergency management is aware and is ready. If they need to close down the school sooner, if they need to close down the road sooner because they know this road will be blocked, so they would avoid any cars, for example, for being flooded, or spending resources on saving people or putting people's lives at danger. If they're closing the road, they're telling people to not to go there, then essentially they're reducing the risk of anybody being at the danger of being caught in the flood. As for the data sources that goes in, so as I mentioned, lots of historical data that would show how the past floods had been, although since a couple of years ago, we are experiencing, 500-year floods happening every year, or 100-year floods happening every year. So the landscape, pun intended, is changing, but still having the historical data, the hydrology data, and the flood maps would be important. And then the physical data, the 2D, 3D mapping, topography, SAR data, and all of that. In addition to that, we're incorporating, sensor data, rain gauges, depth flow, soil composition, tidal height, and all of that information. And then digital data, weather forecasts, with virtual rain gauges, other third-party systems. So we're combining these to create a flood simulation, and then, more of like a ground truth. So the historical and physical data will lead into flood simulation. The sensor data and digital data will lead to creating a ground truth of what's happening at the moment. And then combining all of that, putting all of that into this, digital twin capability and platform that we've created, enables to have a holistic view of predictions for flood, inundation, and water levels and impact to the environment. As for the prediction, so it's very important to note that there are really three components, three kind of calculations that needs to happen. One, as I mentioned, historical data is very important. So past casts help us to better understand and recreate past flood events, and it's not, with our capabilities, is not very difficult. It doesn't require a lot of data. So just understanding, date, time, and having digital elevation maps and better understanding what the rain was at that time, we can create past events. And then nowcast is really the ground truth. It's what's happening right now. So having the sensor data in place with all the other static and underlying data sources, we create the nowcast. That's what's happening. Nowcast and pastcast both feed into futurecast or forecast. And the futurecast and forecast are those hourly forecasts that shows how this is moving. So the simulation, and then that digital twin capability that shows how the flood and the inundation is changing hour by hour as rain forecasts may change, or as the sensors may show additional information or new information, or things are not going as we expected it. The future cast is automatically updated because based on the nowcast data that is coming in. This is a sample architecture diagram that shows how hardware, software, and cloud implementation is working together. The components of the SaaS and the cloud environment, in this case being Microsoft Azure, and also the LoRaWAN network. But essentially, one thing that I call this, the maze of complexity. And one thing that I want to take it away is that the architecture is in place, so then it can be used for, it's a blueprint that could be used for any additional solution. So if it's going to be a wildfire or any other solution, the architecture can be leveraged for that. And really, this platform is based on SAS analytics for IoT. So The SAS analytics for IoT capabilities includes of easy to deploy sensors, so the sensors can be deployed and then can be the SAS analytics for IoT has the data model for to be able to ingest sensor data specifically for the design for digesting sensor data. So connecting the sensor resources so that being able to get that data digested, prepare it, and monitoring. That is about integrating with existing processes and systems. So in this case, the end customer, the end users are cities and municipalities, local government, or state emergency management systems. So how we can plug this system, and the SAS platform enables that to be able to plug the system easily with the existing processes. And then additionally providing predictions and alerts of possible flooding that could go into their case management or work order, or providing alerts in terms of into other third-party system in terms of I'm expecting to see 6 inches of water at this latitude and longitude on hour 6. But on hour 7, this is going to go to suddenly is going to go to 12 inches of water. So these kind of alerts are created and are sent to any type of third-party system. Could be text messages, emails, reports, any of that the agencies and end users are using. So essentially, that was really a summary of how we are applying AI and IoT and really creating a digital twin of being able to monitor, simulate, model, and predict flood events, and being able to provide a decision-making tool for the community and for emergency management to better understand how any flood event would impact the community, what time will impact the community, at what extent it will impact the community, and then what's the exact location that this would be impacted. Yeah, that's it. And so with that, additionally, I wanted to just provide a little bit of information, if it's possible, about the SAS hackathon that we have. And so any of the users of this community, you can communicate, and you can use SAS hackathon as a way to, if you're interested to solve any AI related use cases with your own data, with your own patent, and then just leverage the SAS platform, SAS IoT platform, or any other platform for solving AI usages, you can absolutely use that. So I just wanted to also promote this one as well.
Awesome. Yeah, we'll be sure to pass the word along and reshare on the LinkedIn company page and the email. Yeah, I'm just curious. Excellent work. How is it going to be rolled out, or how many pilots are currently in play?
So this is an existing solution. So there are several cities in the United States, in Europe, and in Middle East that are applying this solution.
And what's the expansion effort, or how do you select and prioritize new deployments of the solution?
Well, it's based on the need. So if the customers, or if their city or any agency, their emergency management agency has a need for this one, we work with them in terms of deploying it. We actually also developed a patent in terms of where is the optimal location to put sensors. So for example, for a large scale area, it may not be feasible to put sensors every 100 feet. And so this is all about how being able to minimize the amount of investment. But the solution is constantly being worked on and upgraded in terms of the user interface and capability. But then the core capability exists, and is been deployed and operational.
Curious about the the power source of this, and how do you maintain like a redundant power system for it if it's deployed in a distributed manner?
So our main capability is on the platform itself. We work on third-party sensor providers. So they are the ones that would deploy the sensors in place. This is more of a cloud-based solution that
Mm.
we connect to the sensor data that already exists, or it's been implemented, and we get that data feed to run the analysis and simulations in real time. So essentially, the solution is a cloud-based solution, but the sensors are LoRaWAN, usually LoRaWAN, that could be deployed by any sensor provider. It's up to them as it relates to power source.
And the forecasting solution is also is that data shared, or are those alert systems shared with the municipality or the area? That
That
they
goes into the municipality or the end customer directly. So they would choose to share it with their users or any other community. Yeah.
Awesome. Um, yeah, I have no further questions. If there's anybody that would like to ask a question, feel free to do so. Um, Otherwise, I'd love to learn a little bit more about the other projects you're working on in a future presentation.
Yeah.
Um,
Thank you for having me.
Thank you, Kathy. All right, so we'll take a break. The next presentation is not gonna materialize, so we'll have a 45-minute break, and then we're gonna get back to Danny Diaz. So we'll see you soon.